we're going to finish up complex numbers. We're going to look at something called Euler's equation. And then here on in, I'd like to describe the material we are going to look at as foreshadowing things you might get in calculus and beyond. It will not be emphasized on the final. If anything, something might show up in an extra credit. But it's the most interesting stuff in the class, I think, if we get to it. All right. That being the case, let's talk about Euler's equation. I'm not going to go right for it. I'm going to try and back into it a little. We know how to do all sorts of operations with complex numbers. We know how to add them, multiply them. On Wednesday, we learned how to find a square root or a cubed root of a complex number. There's one thing we've left off, which is, what would raising some number to a complex power be? That's not really clear even what that means. But we can simplify this question a little. If z is a plus bi, and assuming this follows the laws of exponents, which wouldn't be much use if it didn't, then we know that capital A to the small a plus bi would be capital A to the small a times capital A to the bi. And this, we understand that. We know how to raise a number to a power. It's an integer power. That's easy. If it's a fraction, we know what to do with that also. It's a real number. Well, we pull out our calculator and it gives us that value. So really, this is the kind of a funny guy. And I'm going to write this for reasons that will become clear. I'm going to write this as phi theta, where theta is just some variable. So I'd like to suggest as a candidate for what this is. I mean, we know. Unless this produces some unknown creature, something beyond complex numbers, we should get some value. Let's say x plus yi, some complex number. So I'm going to put forth as a candidate something we looked at on Wednesday. I'm going to suggest this might be equal to the cosine of theta plus I times the sine of theta. I'm just pulling that out of a hat. All right, well, it would be nice if this behaved the way we would want it to. And so that's the first thing we're going to look into. So let me treat this. Let me call this f of theta. And let's see if it behaves the way we would expect when we multiply. So let's take a look at f of theta 1 times f of theta 2. theta 1 would be cosine of theta 1 plus I sine of theta 1. And f of theta 2 would be cosine of theta 2 plus I sine of theta 2. And now I just want to FOIL these and see what happens. All right, the firsts will give me cosine theta 1, cosine theta 2. The lasts both have an I in them. I squared is minus 1, so this is going to be a minus sine theta 1, sine theta 2. Okay. The inner and the outer both have a factor of I. So I'm going to factor that out right at the beginning. And what am I left with? I'm going to have sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. And now I'm going to look at these two groups independently. Now, I hope for some of you, you see a pattern here already, something we looked at. Anyone see a pattern here? Cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. Does that look like anything familiar? Should. This is just cosine theta 1 plus theta 2. This is the addition formula. Or one version of the addition formula. Right? What about this guy here? Sine 1 cosine 2, cosine 1 theta, sine theta 2. That's also an addition formula. That's just the sine of theta 1 plus theta 2. So now I'm back in form of this function, but now what I have is f of theta 1 plus theta 2. That is my that is what I'm proposing as a possible answer to this question, what is a to the I theta, has the right property of exponents, which is that when I multiply these two values, I just add. Right? That's what we want from exponents, right? All right, so that suggests that this was a good idea. If only I can find the value of a, right? A is some number. Then this will work. Well, this is where I run out of road here. In order to show what A is, we need a little more math than we have. When you take calculus, it's very easy to show that A actually takes on that enigmatic value E, approximately 2.71828 goes on. This is called Euler's formula or Euler's equation. Like the constant E, it's named after a famous mathematician, Leonhard Euler. who lived in the 1700s. And this is his famous equation. It also has this other interesting feature. If we set theta here to pi, we end up with the equation e to the I pi. And then we put pi into this, we see cosine of pi is 0, sine of pi, wait a minute, cosine of pi is -1, sine is 0, so this is -1. This is known as Euler's identity. It has the feature, it's considered one of the most famous equations in mathematics. It's kind of the E equals mc squared in mathematics. So, now we know how to raise a value to a complex exponent. All right, any questions? That's going to be the end of complex numbers. And then we'll move on to, as I said, some foreshadowing. Right. Let me start by asking, has anyone here not seen vectors before? Okay. Right. Is anyone here who has seen vectors before not know what the dot product is? Okay. All right. We're going to look at vectors. And we're going to go through this kind of fast, but I wouldn't, do your best to keep on top of it, but I wouldn't worry too much about it. Let me start by saying that what most of you, say vectors. What most of you have learned about vectors is what physicists and scientists use vectors for. A vector, we usually represent it as a line segment with an arrowhead. It has a starting point and an ending point, ending coordinate. And we give the starting point a name. We can call this the tail of the vector, and where the arrowhead is, we'll call that the head, or sometimes it's called the tip of the vector. And what this represents is two things. It represents an angle, right? The direction that the arrow is pointing indicates an angle, which we'll measure the usual way, counterclockwise from the x-axis. And it has a length, which we refer to as the magnitude or the norm of the vector. We have some notation for vectors. For a variable, typically we'll put a little hat on top of it with an arrow. If you look in the book, they use a different notation, which I can't really do on the board very well. They'll just use boldface to mean a vector. And then we have a name for the magnitude of the vector. We call it the norm. And we reuse this notation that gets overused a lot in mathematics, of two vertical bars. This is not the absolute value. It's not the square root of the product of the complex number and its complex conjugate, but it has a similar meaning. Right. We can also represent a vector by describing its endpoints. So, for example, I could have a vector that goes from the point 3, 4 to 5, 7. Those are Cartesian coordinates. But as I mentioned, the only thing that's important about a vector that we're looking at is its magnitude and its direction. So as long as you don't change those, you can move it around. And you could do that by, you could add a quantity to the x component, and you could add a different quantity to the y component. And you can move it around, but it's still the same vector. It still has the same magnitude, the same direction. In particular, you could move it so that its tail is at the origin. It's quite easy to do here. We're just going to subtract 3 and 4. It's supposed to be a 7. And now we have a vector who starts at 0, 0, and goes to 2, 3. And we're going to write this, since we know it starts at the origin. We're going to call it a position vector. It's just the representation of that vector. The vector could be anywhere. We call that a position vector, and we write it using this notation, angle brackets, 2, 3, without the origin. And this is called the component form. The reason we give it that name is, you think along the x-axis, well, here we have a 2, and along the y-axis we have a 3. These are the components of the vector. I guess it'd be good to know what we mean by that. If I have two vectors, v and u, and I want to add them, well, here's what I mean graphically by adding them. If I start with my vector v, I have a vector u in a different direction. And what I want to do is, I can do this either way. I can place the tail of u at the head of v, or I can put the tail of v at the head of u. When I do this, I get a parallelogram. And my new vector, u plus v, is the vector I get when I go from the tail of the original vector to the head of the other vector. So that's how I add vectors. If the vectors happen to be in the same direction, it's a little easier. The direction doesn't change. You just add the magnitudes. And if the vectors were in opposite directions, well, the resultant vector would be just a shorter vector. Okay, so now's a good time to look at, well, why is this component vector form so nice? Well, I have, do something a little more exotic. If I have some vector u here, and it has x and y components, and I want to add it to some vector v, which also has x and y components. So this is ux, uy, dx, dy. I can get the resultant vector just by adding ux plus vx, uy plus vy. So for example, if I have two vectors, let's say 1, 3, and I want to add that to -2, 7, I just add the components, right? It's just -1, 10. I don't have to do any graphing, drawing of lines, or calculating of angles. All right, everybody with me so far? Well, I want to make one more comment, which is, if I have a vector in component form, say a, b, right? So this is my a, and this is my b. You can see right away, using the Pythagorean theorem, that the magnitude of this vector, or its norm, is just going to be square root of a squared plus b squared. We've seen this form in both trigonometry and also when we were talking about polar coordinates. So again, another nice feature of the component form. We can extract from this, we can extract the angle. We know that theta is going to be the inverse tangent of the y over the x component. However, we have to be a little careful now. A and b can be positive or negative. So we have to keep track of the fact that if they're both positive, it will be in the first quadrant, and our arctan function would give us the right value. But in the other quadrants, like say the third quadrant, you would also get b over a would be positive, and you would get not the angle itself, but its reference angle, and you'd have to adjust. So you know, if you're in the third quadrant, you would add pi. In the second quadrant, you would subtract this value from pi, and then in the third quadrant, you would add 2 pi to it. All right. Okay, so now I want to back up a little, and I just want to give you a little bigger picture on the matter. As I said, this is the kind of vector that we use typically in science, in physics. If you asked a mathematician, are these vectors? They would say, yeah, they are. But to a mathematician, this is one type of vector. Right? There's a kind of a broader category of things that are vectors. And what's important is not so much how we represent it, but how they operate. Right? I'm going to be more explicit about that, what I mean by how they operate. But I just want to mention that if you go on in math, you're going to run into something a little bit general, and you shouldn't get shocked when the pointing arrows and the angles go away, and you're dealing with a more abstract object that mathematicians call vector. Right. I guess I'll mention at this point, not that this is the way we add any kind of vector, but that we can add vectors. That's one of the operations we can do on any vector. Another operation we can do with vectors is we can do scalar multiplication. Okay. So I want to emphasize this word here, scalar. Scalar it's a synonym for number. We say scalar when we want to emphasize we're dealing with a number, not a vector. There's no reason to do this, but we do it. So what I'm talking about here is just multiplying a vector by some value. If I multiply it by a positive value, it's going to stretch the vector out or maybe squeeze it down. If the number is less than 1, it's greater than 1, it'll increase it. If I multiply it by a negative number, that just reverses the direction along with multiplying it. So, in particular, we have -1 times vector, or opposite vector. It's just this vector in the opposite direction. When we're dealing with components, we want to multiply a vector times a scalar, where I already have that v is a over ab. Again, it's very easy to multiply. We just multiply the constant by the components. So another reason the component form is a nice form. Being able to multiply by a scalar brings up an interesting member of the family here. If I have some vector and I multiply it by 0, right, my components are going to be 0, 0. And I get what we call the 0 vector. The 0 vector is a strange animal. It does some of the things you'd expect. Right? If you add the 0 vector to another vector, you just get that vector back. But the 0 vector has no magnitude. So you ask, well, what's its direction? Well, depending upon the context, it has no direction, or it can have any direction. Right? If you add the 0 vector to some vector, it doesn't change the direction, so in that sense it's in the same direction. But if you just have a 0 vector sitting out there and you say, what direction is it going? It's not really going in any direction, it's going in every direction. Something to keep in mind, the 0 vector is not the number 0. You can't add a number and a vector. You can't add a number and a 0 vector. I'm sorry, you can't add a vector and a 0 vector. I said that wrong. These are just different animals, so you have to keep them separate. All right. This brings us to one more operation we can do with vectors. If I have some vector v, some vector u, I can subtract u. And how do I do that? Well, I do things that I know how to do already. I can add to a vector, I know how to do that. And I can multiply my u vector by -1, that's something I know how to do. So that's what v minus u is, it's just v plus -1 times u. It's good to look at that graphically. I have my v here and my u here. Recall that this would be v plus u along the diagonal. Minus u would be down here. And when I add minus u and v, that gives me, let me draw this very well. I get a vector like this, but if you look at the geometry here, I could just as well move this over here. It's the other diagonal of this parallelogram. This is v minus u. All right, so now I can do things I want with vectors. I can add them, subtract them. I can multiply them by a scalar. Starting to sound like they have some properties that I associate with numbers. And this is true. You can kind of enumerate them. If I want to say add two vectors, I get a vector. It's called the closure property. If I want to rearrange the vectors, the way I add them, I get the same thing. That's the commutative property. I have three vectors I want to add. It doesn't matter which order I add them in. That's the associative property. I guess given more time, we could actually prove these. The obvious way to prove these is to use the component form, because then these properties of vectors start to look like properties of numbers, right? Properties of components. We also have the zero vector, which doesn't change a vector when you add it. We call that the identity property. And also we have an inverse of a vector, which has a property you add it to a vector, and you can add the inverse, it undoes it. And one way to think of that is that if we add the inverse vector to the vector, we get the zero vector. We have some other properties now that aren't quite the same thing as with numbers, because with numbers you just have one animal, you have a number. But with vectors you have both the vectors and some scalars you can multiply them by. So in particular, we have some distributive properties. If we're adding two vectors and we multiply that by a constant, we can multiply first and then add. and we get the same thing. But there's another distributive property. If we're adding two scalars and then multiplying by a vector, we can also distribute the scalar over the vector. These are both distributive properties. A few more just kind of incidental things. We can multiply 1 by the vector and get the vector back. That's an identity property of multiplication by a scalar. We have this feature that if you multiply any vector by 0, you get the 0 vector. And we also have the fact that multiplying any scalar times the 0 vector also gives you the 0 vector. And then there's one other useful property that we run into now and then, which is if you have a vector, which is a scalar times some vector, and you look at its norm, that's equal to the absolute value of the scalar times the norm of the vector. This is very poor notation, because here the double bars mean one thing, here and here. They mean the norm of a vector, the size of the vector. And here they mean just what we are used to, the absolute value. Poor notation, you just have to know that's what it means. Going back to what I was saying about how vectors operate, when you're dealing in math with a vector, we don't care that it's this pointing arrow thing with an angle. What we care about is that your objects, your vectors, operate this way. And if they operate this way, they're vectors. If you look at the whole world of those vectors, all the possibilities, we call that a space, or a vector space. So, okay. Just a few more things I want to talk about vectors today. We have this concept of a unit vector. A unit vector is very simply, it's some vector v whose norm is 1. They should use u. This is copacetic u. Unit vector has a norm of 1. It just has a length of 1 in whatever units you're dealing with. If you have a vector that's not a unit vector, and you'd like a unit vector in the same direction as that vector, it's very easy to produce that. Let's say I have some vector v whose norm is not 1. Right? Say v is 3, 4. If we take that vector, and divide it by its norm, or multiply it by 1 over the norm. Right? Remember, this is a number, scalar. Then you get a unit vector. Let me demonstrate. I have this vector v, divide it by its norm, which is the square root of 3 squared plus 4 squared. That's 9 plus 16 is 25, the square root is 5. So v over the norm of v is going to be 3/5, 4/5. Right? And I claim this is a unit vector. Well, that's easy to check. What's the square root of 3/5 squared plus 4/5 squared? Well, that's the square root of 9 over 25 plus 16 over 25. That's the square root of 25 over 25. Which is 1, so its norm is 1. Okay. The reason I bring up unit vectors is that there are two very important unit vectors that we deal with a lot. They're so important we give them names. I'm quite sure it was physicists who gave them names, or maybe engineers, because their choice of names was unfortunate. One of the vectors we call I. It has nothing to do with complex numbers. You just have to know that. I is the vector 1, 0. That is, it's just length 1 in the x direction. And j is the vector 0, 1. That's just length 1 in the y direction. All right, why are these so important? Well, you have some vector in component form. You can represent that as the scalar a times I plus the scalar b times j. This is what we call a linear combination of these vectors. When you think of, you may have heard there's a class a little beyond calculus called linear algebra. It's the same linear, right? Okay. Few more kind of connections here. I'd like to connect, just trying to actually write it out, connect these vectors back with some of the trig we've been doing. We saw that the norm of the vector is the vector AB. The norm is the square root of a squared plus b squared, and that the angle theta of the vector is, it's sort of the arctan, inverse tan of b over a, with that adjustment for which quadrant it's in. But if that's the case, we can go in the other direction too. We have a vector here. X component is A, its Y component is B. You can see using our trig functions that, and its length here is the norm. We can see that A over the norm of V is what? The cosine of theta. So A is just the norm of V times the cosine of theta. And B will will nicely be the norm of v times the sine of theta. So we have some equations that allow us to go back and forth between the magnitude and the direction and the components. Lastly, we can use this this notation here, and we can write kind of the decomposition of a vector. Well, it's A, but that's the norm of v times cosine theta times my unit vector I plus the norm of v times the sine of theta times my component vector j. All right, there's a little more to talk about. On Monday, we'll get into the dot product a little bit. There's something else I want to say about this, though. I think. Yeah. Well, let me just say that, using cosines and sines and angles, that obviously has to do with the fact we're using these pointing line segment vectors. But I made the claim that vectors can be different from that. And so this probably would not apply. And I'm hoping maybe on Monday we'll kind of see what it's replaced by in the more abstract sense. Okay, that's it. Remember, if you want a review on Wednesday, come in with something for review. And if you have homework, turning it in. I'm crazy, but I will accept homework as we start the exam.